Hi students, this is a lecture on section 12.6, which is cylinders and quadric surfaces. Now it's difficult to do graphs, particularly in an online class, so these problems are going to be multiple choice where you choose the correct graph, but we will be doing the graphs of both cylinders and quadric surfaces. And I got you a nice image on Canvas, well, a couple of nice images. So if you look on the page called Image, Cylinders and Quadric Surfaces, we have pictures of the different graphs that we're going to be dealing with in this section. So first of all, what are cylinders like? Well, cylinders are going to be an equation that's missing one of the variables. So for example, on our image here, we have the graph of the cylinder y equals x squared. Okay, this cylinder is actually missing the z variable. And so as you can see, this graph looks like the graph of y equals x squared, but because it's missing z, the graph goes up and down parallel to the z-axis. Okay, and in general, a cylinder is just going to be missing one of the variables. So it'll either be missing x, or it'll be missing y, or it'll be missing z. And whichever variable it's missing, that's the axis that it's going to be parallel to. So here, y equals x squared is missing z, and you can see that this cylinder is going up and down parallel to the z-axis. Okay, and then the other images we're going to be dealing with, aside from cylinders, is quadric surfaces. Now, what are quadric surfaces? Well, let me write it on your on the board here. So we just said cylinders. Cylinder is missing one variable. Missing one variable. Okay, so like in that example, we were missing z. Whereas a quadric surface actually has all three variables. Has all three variables. Okay, so it has x, y, and z in the equation. Okay, and in particular, to be a quadric surface, the highest power has to be the second power. Okay, so to be a quadric surface, the highest power is 2. Okay, so quadric surfaces have all three variables. That makes them so they're not a cylinder because they're not missing a variable. And then the highest power is 2, and that means for all the variables. So you can't have any third power or fourth power or any of that. Okay? So going back to the image here, here's an image from our book that shows all the different quadric surfaces. So let me zoom out a little bit so we can see it. Okay, so these are all the graphs of quadric surfaces. And looking at these equations, you got ellipsoid, elliptical paraboloid, elliptical cone, hyperboloid of 2 sheets. So you got hyperboloid of 1 sheet, hyperboloid of 2 sheets, and then hyperbolic paraboloid. Now keep in mind that everything is open book, open notes, so you'll be able to go back to this page when you're doing the homework and the quiz and the test. So you can use this image to help remind you so you don't have to memorize all these different shapes. But the basic idea is, notice that the highest power for any of these variables is the second power. Okay? And with an ellipsoid, you have x squared plus y squared plus z squared equals 1. And then this a squared, b squared, and c squared, these are just going to be numbers. Okay, with the elliptical paraboloid, you have an x squared and a y squared, and then on the other side you don't have a z squared. So there it's actually z to the first power. With an elliptical cone, you have an x squared, a y squared, and a z squared, but the z squared is actually on the other side of the equation. So that's the difference between ellipsoid and elliptical cone, is the z squared is on the other side, and you also don't have a constant term for elliptical cone. And then for hyperboloid, you have an x squared, a y squared, and then you're subtracting z squared, but then you also have a constant term on the other side, which is 1. Okay? That's a hyperboloid of 1 sheet. And then for a hyperboloid of 2 sheets, you have z squared minus x squared minus y squared equals 1. So you're subtracting twice here. So you have a z squared, an x squared, and a y squared, but you're actually subtracting both of those. Whereas notice with the hyperboloid of 1 sheet, you're adding one of them and then subtracting the other one. Okay? And notice that with the graphs, the hyperboloid of 1 sheet is called a hyperboloid of 1 sheet because looking at it, you have one continuous sheet of the curve, whereas for the hyperboloid of 2 sheets, notice we actually have 2 parts to the graph. So we have this part on the top, and then we have the part on the bottom. Okay, and then for the last graph, we have a hyperbolic paraboloid. That one is y squared minus x squared equals z. So that's very similar to the elliptical paraboloid. It's just the only difference is here we're subtracting rather than up here we're adding. And keep in mind that with any of these graphs, you can switch the variables around. So it doesn't, for example, hyperbolic paraboloid doesn't have to be y squared minus x squared equals z. It might be x squared minus z squared equals y. Okay, so you can move those variables around as you wish. But those are the 6 basic graphs you have here. And when you're doing your homework, because these can be difficult to sketch by hand, I'm going to recommend that most of you are probably going to want to use an online grapher called Geogebra. Okay, and Geogebra is, you can just Google it, go to Geogebra, and you want a 3D grapher. So just do Geogebra 3D, Google that. Okay, and then 3D calculator is what we want. Alright, and then it gives you this 3D calculator, and you can actually just type in equations. So for example, the first thing we're going to be trying to graph here is going to be x squared plus y squared plus 9z squared equals 36. Equals 36. Okay, so x squared plus y squared plus 9z squared equals 36. And as you can see here, this is very handy because it instantly graphs the whole thing for you. So then you can just try to decide which picture it is. So just looking at this graph, we can see that it looks kind of like a big squash ball. And you can actually drag it around a little bit if you want. You can look at the whole graph, which is really handy. And you might be wondering which axis is which. I believe the red one is the x-axis, if I'm not mistaken. But it'll be clear to you that the blue axis is always the z-axis. And then the red and the green are the x and y axes. Okay? But looking at this graph here, how do we know which picture it is? Well, we go back to our image. We look at these images. Which one does it most look like? Well, I would say it most looks like the ellipsoid. It looks like the ellipsoid, but it's been greatly squashed down, and that's okay. Remember, this ellipsoid can be any sort of shape as long as it roughly looks like a, kind of looks like a football here, whereas this one here looks like a squashed football. but it's an ellipsoid because it has cross sections that are ellipses and ellipses or circles. Okay? All right. So for our first example, I'm going to go ahead and do that graph I was just talking about. Okay, the one I just entered into Geogebra. And most of you probably want to use Geogebra. It makes these homework questions a heck of a lot easier. Okay? So example, determine the graph of each equation. Determine the graph of each equation. Okay, and our first equation is going to be the one that I just typed into Geogebra. Okay, so our first equation is going to be x squared plus y squared plus 9z squared equals 36. Okay, x squared plus y squared plus 9z squared equals 36. So again, the easiest way to do this is to just go ahead and go on Geogebra, the 3D graphing calculator, and type in the actual equation. Look at your picture, and then looking at your picture, you go back to our image, and we look for which picture it most looks like. Well, of these graphs, it definitely looks the most like an ellipsoid. It looks like a football. It just looks like a football that's been deflated or completely squashed. But it's definitely an ellipsoid. So Geogebra takes a lot of the guesswork out of it. So the easy way is use Geogebra 3D. And from that one, you use Geogebra 3D to get the good picture. And then when you're doing your homework, you're just going to select the graph that most looks like that picture. Okay, so here you would select the graph that looks like a squash football. Okay, so for this one, you're going to use Geogebra 3D, and we decided that it's actually the same as an ellipsoid by looking at this image. Okay, so this is going to be an ellipsoid. Ellipsoid. Okay, and keep in mind on your homework, it will be multiple choice, so they will have 3 or 4 graphs, and you're going to have to choose one of the graphs that looks like the one that you drew. Now, of course, that's pretty easy to do. When you're using the Geogebra 3D, you can see pretty clearly what the picture should look like. And you can even click and hold to drag around and look at the graph, so you make sure you choose the right shape. Okay? And then just for this first problem, I'm going to show you the hard way of doing it. Now, I don't recommend that most of you do the hard way, but this is how people used to do it. Okay? So, the hard way, which is probably not recommended, but this is the old-fashioned way before people had graphing utilities like Geogebra. The hard way is sketch a graph of each cross section, and then you combine those cross sections to obtain the final graph. Okay, so you sketch a graph of each cross section and then you combine. That's kind of the old-fashioned way. This was before people had before they had modern graphing calculators that would graph everything for you. So this can be time consuming, so I'm just going to be doing it for this first problem. We've already seen the graph for this problem because GeoGebra drew it through for us instantly, but we're going to use cross sections now. So how do you draw cross sections? Well, it can be quite tedious, but the basic idea is you set each variable equal to 0, and then you sketch into your graph. Okay, so for our graph, you want to draw your x, your y, and your z. So remember that the vertical axis is z. This is z. Your horizontal axis is actually y. And then the axis that comes sort of out at you, like this, that's x. Okay? And to sketch a graph of each cross-section, what that means is you're actually going to set each variable equal to 0 and find the cross-section for that plane. Okay? Okay, so we're going to set each variable equal to 0. Set each variable equal to 0 and graph. All right, so that could be difficult, but let's go through this. So for this problem, we have three variables. We have x, y, and z. So let's start by setting x equal to 0 to get our first cross-section. Okay? So first off, in red, I'm going to set x equal to 0. Okay, so if I set x equal to 0, then we're going to be graphing, this is going to become 0 squared, so we're just going to have y squared plus 9z squared equals 36. Y squared plus 9z squared equals 36. Okay? And if you don't remember what this graph is, if you have two variables added together, each one is a square, but then you have a number here on one or both of these, this is going to be an ellipse. Okay? This is going to be an ellipse. And again, even if you don't use GeoGebra, you probably at least want to use a graphing calculator, like one that you have, a real graphing calculator that you can have in your hand. But this is an ellipse, so what is this going to look like? Well, what the 9 does is it means that it's going to be shorter along the z-axis and longer along the y-axis. So in red here, a sketch of this ellipse is going to be an ellipse along the y and the z-axis. So it'll look something like this. Actually, that was pretty terrible. Let me try that sketch one more time. Yeah, that's not my best drawing, but what it is it's supposed to be an ellipse, and it's supposed to be skinnier than that. So let me try one more time. There we go. I don't know why I had so much trouble with that. But as you can see, it's difficult to sketch these by hand. But the cross section that we just did there was when x is 0. That's going to be the cross section on the YZ plane. That's the YZ plane cross-section. Alright, and if you want a more accurate ellipse, you can use a graphing calculator, obviously. But I don't want to go through the details of trying to draw a perfect ellipse when basically we just want a sketch of it. Okay? So that's on the YZ plane. So when you set one of the variables equal to 0, then it's going to be on the other two variables for that plane. So that's this plane here, right on the YZ axis. Okay, and then we'll go ahead and go through the other cross sections. So for the other cross sections, let's do y equals 0. So if we set y equals 0, what do we get here? Well, if you're setting y equal to 0, then you're going to be on the other two variables plane. So that's actually going to be the xz plane. So you got the YZ plane on the last one, and this time we're on the XZ plane. Because if y equals 0, then that means you're restricted to the XZ plane. Okay, so if I set y equals to 0 here, our equation is going to be x squared plus 9z squared equals 36. Okay, so x squared plus 9z squared equals 36. And this one is also going to be an ellipse. And again, GeoGebra is like way easier than this, obviously. But so this is going to be an ellipse on the XZ plane. So when I sketch this one, it has basically the same equation as the last problem. So it's going to be shorter along the z-axis and longer along the x-axis. Okay, but now we're on the xz plane, which means we're in this plane here. So now I'm going to go ahead and sketch another ellipse in blue that goes way back here and way up here. So that's going to look something like this. Okay, again, not the best drawing. As you can see, I struggle with drawing these, particularly on the blackboard. But that right there, that's our other ellipse. That's the blue XZ plane. Okay? And then the last cross section that we would do is we would set z equal to 0. Okay? So if we set z equal to 0, then that's going to put us on the xy plane. So the plane is the other two variables. So here if z equals 0, the other two variables are x and y. So we're in the xy plane. And if we set z equal to 0, then our equation is actually going to become x squared plus y squared equals 36. Okay? X squared plus y squared equals 36. And because this one doesn't have a number in front of the variables, this is actually going to be the equation of a circle. Okay? So this one is a circle. And this is going to be a circle in the xy plane. So I'll go ahead and sketch this in green. And the radius of this circle is going to be the square root of 36. Okay? So our radius is actually going to be 6. So circle, radius 6. But again, we're just doing a sketch here. It doesn't have to be perfect. But as you can see here, we're talking about the xy plane. So now we're talking about this horizontal plane. And I'm going to do that in green here. And keep in mind that your graph needs to go through the other graphs, so that actually makes it easier to sketch. So what we're going to have here is a circle that needs to go through all these other graphs for it to make sense. Okay, so it's going to look something like that. I know that's a terrible picture, but even so, I think we can kind of see the squash football shape. So if you look at our final graph here, you've got a squash football. It might be a little hard to see because I'm not the best at drawing, but if you imagine this as a squash football, I think you can see the shape. Anyway, this is what people had to go through all the time before they had GeoGebra. But as you can see, GeoGebra does all that for us instantly, and we can even move the graph around to look at it. But as you can see from above, we do have a circle. So the red and the green axes are the x, y plane. And then from the side, it's squash. So from the side, you have an ellipse here and an ellipse there. And those two ellipses combined together, along with the circle, gives you an ellipsoid. Okay? Cool. So that was that's quite a lot of work to actually do the cross sections. So I don't recommend that you actually do cross sections too much, because it can just be a ton of work for each problem. And you do have 13 homework questions, so that can get to be a little bit much. Okay, so from now on, I'm going to be doing the easy way, which is on GeoGebra. Okay, so for our graph there, we got our squash football, and I probably could have sketched it better, so let me add a little bit in here. It's actually supposed to be an ellipsoid, which means it should look something like this for my sketch. I just have difficulty drawing on here. But these are all little ellipses here. So it's sort of like a squash football. Okay, probably a terrible drawing. But anyway, I want to do some more examples of using GeoGebra and determining which one is the correct graph. This should probably be one of the easiest things we do in this class, though. Okay, so let's go on to example number 2. Example number 2. Again, they want us to determine the graph of the equation. And for this one, we have 4y squared plus z squared equals 16. 4y squared plus z squared equals 16. So now you guys should probably notice, even without using GeoGebra, that this is missing one of the variables. So if it's missing one of the variables, remember that means it's a cylinder. Okay? So it's missing a variable. So the variable that it's missing is x. So that means it's a cylinder. Right, so the graph is going to be a cylinder. Okay? And then when you're doing your homework, you'll have 3 pictures, or sometimes 4 pictures, and only one of them is going to be the correct graph. So how do you know which one is the correct graph? Well, again, I recommend that you don't do cross sections unless you have a lot of time on your hands. I recommend that you use GeoGebra. Okay, so we would just go into GeoGebra. We would delete whatever we had before, and then we go ahead and type in our equation, 4y squared plus z squared equals 16. And we know it's going to be a cylinder, but without doing cross sections, it takes a long time any other way. So here in our picture, we can see we actually do have a cylinder. And if I zoom out a little bit, you just use your mouse wheel and you move your mouse wheel down to zoom out and you move it in to zoom in. So as you can see here, we actually have a cylinder, and on the YZ plane, which is going to be the green and the blue, we do have an actual ellipse as a shape. Okay, so you have an ellipse here, and then that shape is extended along the x-axis. So the red axis is the x-axis. And the reason that it looks like this is if they don't write down x, that means x can be anything. So it goes forever either direction. Okay, so along the x-axis, it's parallel to that. Okay, so this is a cylinder, and if you wanted to do this by cross sections, it would have been harder. But you know, when x equals 0, you basically have an ellipse, and that's because x doesn't even exist here. And then if you draw the rest of it, it's actually going to be a cylinder. Okay. And I'm probably not going to do cross sections for any of the other ones, so we're just going to use GeoGebra for our graph. Okay. Alright, so I wanted to do another example from this section. Example number 3 is y squared plus 4z squared equals x squared. Okay, y squared plus 4z squared equals x squared. And again, you can do cross sections if you want, but that's a lot of work. So I'm going to go ahead and use GeoGebra. First off, notice that none of the variables are missing. So we know it's going to be a quadric surface. And then it's just a question of which quadric surface it is. And probably the easiest way to decide which quadric surface it is by just using GeoGebra and then looking at the pictures on the image and choosing the correct name. Okay, so let's go through. So we're going to go ahead and type in our equation into GeoGebra. So we type in y squared plus 4z squared equals x squared. And then looking at our graph, it looks a little bit strange at first. But if I rotate it a little bit, remember that the red axis is the x-axis. And what it looks like here is it looks like we have two big snow cones, right? We have a snow cone there and a snow cone there. And they're actually called snow cones because the bottom of the cup is actually a cone. So looking at our images, well, which of these pictures does it look the most like? Well, definitely the elliptical cone. Okay, looks like a couple of snow cones. So our answer is going to be elliptical cone for our graph. We can see that it's definitely that shape. Okay, and of course when you're doing your homework, you're just going to want to pick the graph that looks like that. Okay, that looks like a couple of snow cones with the bottom of the cup touching each other. Okay, and you're not going to actually have to sketch any graphs for this. Remember, it's multiple choice. So GeoGebra makes it a lot easier because then you can drag the graph around, identify the graph, and then choose the correct choice when you're doing your homework, the quiz, and the test. Okay? Alright. So I just wanted to do one more example. Example number 4. Hopefully you won't find these too challenging. I feel like GeoGebra makes these problems a lot more easy than they used to be. before people had graphing calculators and graphing utilities. Okay, so example number 4, we're going to be graphing x squared plus y squared minus z squared equals 36. Okay, x squared plus y squared minus z squared equals 36. So right off the bat, we know that it's not a cylinder because it's not missing any variables. And then, again, the easiest way to do these is to just go on Geogebra, type in your equation, and then identify it looking at the picture. Okay, so x squared plus y squared x squared plus y squared minus z squared equals 36. And here I accidentally have 2 equations typed in. It's acting kind of glitchy right now. So something's not right here. So I'm going to go ahead and close this and reopen it. Okay, so it was glitching out a little bit. That happens sometimes. So I'm going to start over again and then type it in again. So what we had was x squared plus y squared minus z squared equals 36. There we go. Okay, so that's quite a big graph, so I'm going to zoom out using the down mouse wheel. And this kind of looks like an hourglass shape. So looking at this picture, if you drag it around, you can see it looks a lot like an hourglass. And so looking at our images, which of these images does it most look like? Well, I would say definitely the hyperboloid of one sheet. That one looks like an hourglass as well. It's one sheet because it's only one solid. It's only one surface. So definitely a hyperboloid of one sheet. And as you can see, ours is more squished in the middle than the one that they have, but it is still the same shape. So we're going to call that a hyperboloid of one sheet. Hyperboloid of one sheet. All right. And with that, I think you should be good for your homework. And you can always do these with cross sections if you want, but that's a lot of extra work. It could be fun though if you have the time.